some more Griffiths quantum mechanics. So we are getting into probably the most useful example that you'll ever have with quantum mechanics, which is the infinite square well. So an infinite square well is where we can have a particle trapped in exactly what it sounds like, a well. So in our energy versus space, so this would be v of x, and this axis is x. Then what we have is this goes to infinity, and this goes to infinity at the points 0 and a. So this means that we have some potential that looks like two vertical lines, making a well that if we have some particle trapped inside it, it can't ever get out. So just like kicking a ball over a hill, in order to get the ball as a really bad person, in order to get the ball out of the well, you would have to kick it with enough kinetic energy so that it overcomes the potential energy. So my guy will have to kick the ball with enough velocity so that the kinetic energy exceeds the potential energy. If my potential energy V is infinite, it goes to infinity, there's no amount of energy that I can give this little particle to get it out of the well. It's trapped in there forever. So it's an incredibly simplistic example of a particle that is mathematically stuck between the bounds of 0 and a, meaning that our wave function is 0 outside because it doesn't exist outside the well, and it only exists between the spatial point 0 and a. This means that when we say normalize it, we don't need to normalize over all space, we only need to normalize between 0 and a. So that's the real beauty of this example, is that it's so straightforward. Our particle is only here. It's a bound state, in other words. So it has to exist within this potential boundary. It just doesn't exist outside the boundary because that would take an infinite amount of energy to get it out of the boundary. Now, yes, there isn't really anything in nature like this, but because this is so simple, it serves as a great approximation for looking at bound states. So even though, yeah, this is not physically achievable, it's still a very useful exercise to go through, and it's something that really comes up again and again when looking at bound states is, looking at, say, the infinite square well. And we say square because, 90-degree angles versus a potential like a simple harmonic oscillator or something, which I believe is the next example, where like our bound potential is a parabola rather than just a 90-degree angles. First, even though again, what in nature is going to have perfect 90-degree angles like this, where our potential, instead of being like some actual function, is just a vertical line. Even though it doesn't technically exist, it is still I mean, one of the most powerful examples we have in quantum mechanics. So if you are not someone who does quantum mechanics, this square well is really like the first step of where to begin to understand where this is all coming from. Which I know may seem weird if you're not into quantum mechanics and say you're just coming here because you're interested to learn more about it. You'd be, what the hell is this? Why are you talking about this? I just can't overstate the importance of this example. Okay, so our Schrodinger equation looks like this. We have negative h bar over 2m, and I'm going to really try to use full derivatives here. Full derivative, second derivative of psi plus v psi equals e. Or if you look it up online, you're very likely to see this representation. I did an earlier video on it. They are equivalent. Now, inside this square well, so like inside here, we don't have any potential energy. It's just zero. We only have these two spikes of potential energy. So that means that our equation has simplified greatly to this guy, because we were able to just flat out take out that potential. Again, this is a simplistic example. This is what makes it powerful. The power of it is that we reduced it to the simplest possible example. This is not a detriment to it at all, the fact that it is simplified. Okay, now we can rearrange all this junk so that we get second derivative with respect to x. I'm going to move this negative h bar over 2m to the other side times e psi. Now, just flat out simply, there are two reasons to do this simplification here. So I'm going to come up, actually let's just grab a notebook and let's take a look at this. So I have d psi dx squared, and that equals negative 2m over h bar times e psi. Okay. Now, one thing is that it gets, it's h bar squared. It gets a little bit tiresome to write out 2m over h bar squared times e. So, like, one part of this is just flat out laziness. It's much easier to write it, as, say, this is just some constant. Now, I could call it just some constant c times psi, where c equals this. I could also arbitrarily decide that the constant should be a negative, but we kind of have a thing in physics where we don't like to call constants negative, because that sort of hides a little bit of the physics of the problem. I apologize if you just took like high school physics and they really drilled into your head that little g is negative number. That's just sort of, it's a little bit sloppy, and it gets confusing. So for the most part, if we're gonna just call some terms a constant, we usually want to stick with calling them a positive number so that we don't get confused on signs. Now in this case, there's a special thing that happens with waves. So if I have a sine wave, if I took the slope of these, so I would get something very high, I would get a 0, I would get something very high but negative, I get a 0, I get something very high again. What I get is a cosine. If I do the same thing again, I get 0, I get something negative, I get 0, I get something positive, and then I get 0. You will notice that I get a negative sign. So if I take the slope of a sine wave, I get a cosine. So d dx of sine x just equals cosine. And d dx of cosine of x equals negative sine. Meaning that the second derivative with respect to x of a sine wave for x equals a negative sine for x. So if I have the second derivative of something equaling a negative of the same something, second derivative of psi equaling a negative psi, then a solution is sines and cosines. Now the constant comes out because if I take, say, the derivative of sine kx, then we do the derivative of the inside. So that equals d dx of the inside times the derivative of the outside, like sine u, where u du, where u equals kx. So what I get is the derivative of the inside is k, the derivative of the outside is cosine. I do that again for d dx, second derivative of sine kx. Well, that's going to be derivative of this guy. So I take the derivative of the inside, which is a k, and now that's times this k. So I get k squared negative sine kx. Now for this reason, that's why instead of just writing it as c, I'm going to write it as k squared. Why k? Okay, again, if you just took high school physics or like your first semester graduate physics, especially if you took the algebra-based physics, I'm just going to say I'm sorry. I don't know why everything turned out to be a k. It just happened that way. So all I can do is say I'm sorry that k was used in Hooke's law. I'm sorry that k was used in Coulomb's law. It's just a coincidence, okay? For most people in condensed matter physics, k is fairly standardized, and it refers to something called a wave number. Now you may wonder, why do I have k squared, even though I showed you all this? Why would that be better than just having c and then having sine? If we did it this way, then our psi would have to be, something like sine square root of cx. Well, here's the thing. Units matter, all right? This is not math, this is physics. So our units do matter. And a trig function, like a sine or a cosine, cannot have any units inside of it. So that means that k times x has to be unitless. So that means x is space, so we're going to say that has units of meters, meaning that k has to have units of inverse meters, so that we end up unitless. So we cannot have units here. K does have to have a unit, and its unit is inverse meters. It's inconvenient to have something like square root of C has units of inverse meters. It makes more sense to go ahead and use something that has the same power of units as the argument of our trig function. Now, I said units matter. We're saying that K, so if this is true, right, that means that K squared, as I just arbitrarily decided to call this thing K squared, that thing, this is physics, that K squared equals 2m over h bar squared. So the question is, does K, our K, needs to have units of inverse meters? Well, let's see. We have kilograms. So we have mass, right? Oh, you know what? I totally forgot to write my E in there, didn't I? There we go. E. Ah, that makes it much better. So, I have square root of kilograms. And I have square root of joule. So energy is a joule. So I'm going to write out what a joule is. A joule is a kilogram. Whoops, 1/2. So energy comes from force times distance. Force is mass times acceleration times distance. That is a joule. This is the square root of a joule. That is divided by h bar has units of joules times seconds. So that's a kilogram meters squared over seconds squared times a second. Those seconds cancel out. These seconds cancel out. Those kilograms cancel out, and one of the meters cancels out, leaving us with units of inverse meters. Yay! So, what seemed totally, completely arbitrary in calling this constant K squared actually does have a meaning in physics, and we are typically going to be looking at things in what we would call K space rather than real space. So our K is square root of 2me over h bar. You may have noticed if we looked at our kinetic energy term, I could multiply both sides, or top and bottom, by m, and I get momentum squared over 2m equals kinetic energy. So my momentum equals 2m times e, and the square root of that. So I just multiplied both sides by 2m, and then I took the square root, I got the momentum. So my K, my wave number, which has units of inverse meters, is also the momentum divided by h bar. So this is another way when we say graph things in terms of K instead of an X. It's another way of graphing it in terms of momentum instead of like position. So, when we looked at our uncertainty principle, right? Saying that has to be bigger than, like, say, h bar over 2. This is a way of looking at something that's in meters and something that could be expressed in inverse meters. That's one reason why this uncertainty principle comes about, is, doing a straight up Fourier transform. And then you get that factor of h bar in there. So you'll notice if we change that, so if I had, like, say, delta x, delta p, it's probably a more normal way to write it, and then I change that to delta x, delta k h bar, you see we just get those h bars canceling out, and then it does reduce to a purely mathematical construct. Okay, so one reason to rewrite this as k was because we were lazy, didn't want to write all that junk. The other reason is that we're going to be using k a lot. Okay, now our complete solution to this, the second derivative of any function, it being the same function times a constant, that refers to a sine and a cosine both. So I could have done my example with just a cosine, and if I take the derivative of a cosine, that's a negative sine. If I take the derivative of negative sine, that's negative cosine. So, and as we saw in the first part of this chapter, we can always write psi as a linear combination. And then we just have two constants out here, which we have no way of determining yet. So I have no way of determining what these constants are as of yet. All I know is that something that looks like a sine kx plus b sine kx satisfies that equation. So if I did d dx of both these guys, sine kx plus b cosine kx, that's going to equal a k cosine kx minus b k sine kx. I take the second derivative of that guy, and that's going to equal a k squared negative a k squared sine kx minus b k squared cosine kx. And I could, of course, pull out that negative k squared. So I have this guy minus bk squared. I can pull out a negative k squared, and I get negative k squared times my original function. So I have satisfied that differential equation. So this guy is satisfied. We are happy with that solution. Now, from that information alone, we have absolutely zero way of determining what these constants are. They could be 1, they could be 0. Well, I mean, one of them could be 0, but we don't have a way to determine that. But from that differential equation alone. But we have boundary conditions on this guy. So normally, and we'll get into this for future problems, but normally we will have a an issue where both psi and its derivative are continuous. So what that means is that if psi out here up to point 0 is 0, then that means psi in here at point 0 must also be 0. We can't have a psi that has a discontinuity like that. It needs to be the same value. Now normally we would have that not just the wave function has to be continuous, but also its derivative must be continuous, but we're going to worry about that later. Just as he decided to in Griffiths, that's what we're following here. Let's just hold off on the derivative, and let's just keep with the fact that the wave function has to be continuous. So that means that at psi equals 0 and psi equals a, our wave function must be 0. Plugging that in here, so psi of 0 is a sine 0 plus b cosine 0. This equals 0 because sine of 0 is 0, but cosine of 0 is 1, so it just equals b. So what that means is that b has to equal 0. So we found one of our constants from our boundary conditions, meaning that we can simplify our wave function to be a sine wave. Now, since it has to be 0 at a, so psi of a has to equal 0. Psi of a is a sine ka, and that equals 0. The only places where our sine wave is 0 are multiples of pi. So at 90 degrees, or pi halves, our sine is at a maximum. At pi, it crosses 0. At 3/2 pi, it's at a minimum. And at 2 pi, it crosses 0 again. So what that means is that Ka has to follow this sequence. So Ka could be 0, or it could be plus or minus pi, or it could be plus or minus 2 pi. So I could have Ka equals in pi for any n that's an integer. So n is an integer, and it can start starting at 0. So we can have it be plus or minus. So we could say n is an integer, say starting from negative infinity going through 0 to positive infinity, or I could say it starts at 0 and it's plus or minus any integer. So for any n that's an integer. So we can't have, we're not having k equals 0, we're just allowing for a to be 0. So let me write that again. So my k has to equal, or my k whenever I have a ka, that's going to equal in pi, because my well is of width a. So my k, just moving that a over, is in pi over a. For any of those guys, any of those n's. Now, again, we don't know the constant capital A, but without knowing that yet, we know a lot about our particle in that well, because just from this alone, we can find our energy levels. And that's because, as we decided before, K equals square root of 2 times mass times energy over h bar. And we also decided that that equals n pi over a. So that means that 2 times m times energy over h bar squared equals n squared pi squared over a squared. We solve that for energy, and we get energy is going to equal n squared times pi squared times h bar squared over 2ma squared. We just do the same thing to both sides. There we go. So, just getting that far, we didn't even get that far, right? But we were able to determine, without really any trouble, what the energy levels of this guy are. So this is what tells us that there are quantum or discrete states of energy, or energy levels. And this is why we have energy levels, because we can only have specific waves that fit into this cavity. They have to equal 0 at the boundaries. This is exactly like an acoustic sound wave. So like your wind instruments, they have cavities and they have boundary conditions, and you could figure out the fundamental frequency of your instrument. Our next frequency, so we now have different nodes where it hits 0. So our fundamental frequency just has 2. Our first harmonic has 3 nodes, or we could say 2 antinodes. But we are limited in the wavelengths that we can have in our cavity. We can't have a wavelength that looks like that. That is not allowed. This is not that there is a low probability of it being loud. This is just not likely. It is not a we just haven't observed it in nature. No, this is just math. If we have constructed our energy potential well, we are limited in the waves that will fit in it. So this is not a subjective thing. A lot of people like to talk about quantum mechanics like it's just all subjective because it's probability. No, there's a difference. Yes, quantum mechanics is dependent upon probabilities. That does not mean that anything can happen. So we have discrete energy levels because our particle is a wave. And we are able to determine those energies just by this condition. So we determine our energy levels from our boundary conditions. If we do want to know what A is, so let's say I do want to figure out what A is. So my psi equals A times sine kx. I find A from normalizing. So that's how you find A. So our most general normalizing function is we take the integral of our probability density, of our probability So we get our probability density over all space, and our probability of finding our particle anywhere at all in space is 1. Now for the infinite square well, our particle is trapped. It's in a bound state. That means our particle, our wave function, only exists between 0 and a. How do we know it exists between 0 and a? Because we made it have walls with infinitely high barriers. Okay, we're still integrating over x, so we have 0, we have a, and then I have my wave function squared, so that's going to be a squared sine squared kx. That's how we determine what a is. And I don't know off the top of my head what the integral of sine squared is. I would honestly look that up in an integral table. I'm sure I have one. All documents. Exponential integrals, integral table. Oh, looks like those are just Gaussians, which are useful too, but not right now. Okay. I know it's good to do it by hand, but yeah. I'm a little bit lazy there. Okay, so our integral, oh, that's sine. I was going to say that doesn't look quite right. Just sine squared. Did they determine that that's just like too easy to put in a table? Nobody wants to do it? Alright, we'll just get it from Griffiths then. And yeah, it is a over 2. Wow, apparently sine squared is just considered too easy to even need to have it in an integral table. That's funny. Yeah, most people I knew just used, I mean, for basic integrals like this, it's really just remembering them all. I mean, you could always do like a u substitution, and I think that's how you end up solving it, like if you're in calculus or calculus 2, right? You're going to, I believe the method is you use a u substitution or half angle theorem, some stuff like that. Not even going to worry about it. Let's just go back to Griffiths. There we go. Okay, so from Griffiths, we can determine that we had an a squared, and I suppose I should technically put that absolute values there. 0 to a dx, and then that's going to be sine squared of kx, and then we take the result of that as just being a over 2. So that equals 1, and then you just solve it for a squared, absolute value a squared. So this is what we get for our psi. Because you'll notice when we had our k here, our k was also quantized. Meaning that there are infinite numbers of k's. We don't just have one k. our K depends on integer numbers. That's how we get our different energy levels. So we have energy when n equals 1, energy when n equals 2, and so forth. We have an infinite number of possible energies. Infinite number of n's gives us all these different levels. That also gives us an infinite number of psi's. So our psi also depends on n. We get a series of all of these. And you may recall that this was something that Griffiths pointed out before. As promised, the time-independent Schrödinger equation has delivered an infinite set of solutions, one for each integer n. And then we have this figure here, which is nice. I like this sort of visualization where we have our ground state energy that has one antinode, so that'd be like n equals 1, n equals 2. We have two antinodes, n equals 3. That's fun. So we get an infinite number of these states, excited states. Now, they do have some interesting properties, all of these psi n's. One is that they alternate between even and odd. This makes sense. Say this first excited state, psi 1, our highest point is in the middle. So this would be even. Our odd, the middle corresponds to 0. Our next one, our middle corresponds to a maximum again. So that's kind of fun. They alternate between even and odd depending on, well, the n, is it even or odd? So even, odd, even. I tend to just draw them out because you'll notice 1 is an odd number, 2 is an even number. Whatever. If it bugs you, you can redo your indices. Okay, as you go up in energy, each successive state has one more node, 0 crossing, or you could do it antinode. Most of my students, like when we do acoustic waves, prefer the antinode because it's like a 1-to-1 correlation. So this is an antinode where it's at a maximum, and those are nodes. So that has one antinode, psi 1, 2 antinodes, psi 2, 3 antinodes. If you like nodes for some reason, you're always going to have number of nodes minus 1 equals n. Or you would have number of nodes equals n plus 1. So for state n equals 1, we have 2 nodes. For n equals 2, we have 3. Okay, now this is kind of a fun one. All of these solutions are mutually orthogonal in the sense that their inner product equals 0. So if we take the complex conjugate of 1 with some node or some state m and psi with some state n, I mean the complex conjugate part ends up not mattering here because they're real, but what you get is you get your a squared, which was 2 over a, and then you have sine over dx, some m and some n, And when we solve that out, unless m equals n, then it does not work. So for this to be true, so you'll notice this argument does not work if m equals n. So if m is equal to m, then what that means is that, like here, I would get sine of 0. Let's just even ignore the fact that it diverges. We can even do it, I can do it way back up here. I can say that was cosine of 0. So then I got an integral of a 1. And if this whole guy went away and ended up being like some constant, because that whole guy would end up just being integral of 1 over dx would just be x. So that would just be x. So clearly that would not equal 0. So that's the part in all of that proof where that just doesn't work if m equals to n. So kind of a nice way to combine orthogonality and normalization in a single statement is to say that psi state m times psi state n, the integral of that probability density equals a Kronecker delta, which is 0 if m does not equal m and is 1 elsewhere. So that's another way of saying that they're orthogonal or orthonormal, however you want to define that. Well, this would be like it is. This is just saying they're orthogonal. If we combine it with the normalization, we could say they're orthonormal, which, you know, we might as well, right? Okay. The other thing about these solutions is that they are complete, meaning that any other function f(x) can be expressed as a linear combination of them. It's been a little bit of a theme this chapter that we can always have a linear combination. If you've taken like PDEs already, which if you're in a class, if you may or may not have, if you're in a modern physics class where this is like the end of your class, probably square well is about as far as you're going to get in quantum mechanics, which is fine, because you did a whole bunch of other crap in modern physics. So you probably haven't taken PDs yet. So you will recognize one day that this is just a Fourier series. So a Fourier series is basically saying it is redefining a function to be a linear combination of sine waves. So for Fourier series, we're saying that any function f of x can be described as any series of sine waves over an infinite number of integers. So we can take discrete sine waves, add them all up in a linear combination to reproduce any function. So leaving the fact that that exists, I will leave that to other math classes. For the people who aren't in math classes, I will say it's kind of like, say you have a square, that's your function. I can keep approximating it with sine waves until I reproduce what that square is. So I could start off with something like that and then keep adding sine waves until I get closer and closer and closer to that square. It may seem like a dumb thing to do. Why would you do that? And it's because it helps to make problems actually solvable, like even in classical mechanics. So say heating up a rod. So say you have a rod and you have some fire. So metal rod and fire. If we wanted to model the way that the heat is distributing through there, we use a Fourier series, because we end up with that exact same example. But if you remember from math, a vertical line is not a function. So we kind of have to approximate it, and then we approximate it closer, and then closer, and then closer. It's one of the ways that we go from analytical solutions to numerical solutions. So we're, instead of expressing something as just a function that in many cases is not even solvable, we write it out as a series, and then we truncate the series at some point at which it is solvable. So we take something that's very complicated and we break it down to an infinite number of less complicated pieces, and then take a subset of those infinite number of solvable pieces. Okay, so that'll be left to, unfortunately, your other math classes. And then here, I think he just has, like a determining your constant through I don't know how to say that properly, Dirichlet theorem. This is just your method of solving this guy for your constant. So I can take my function multiplied, like my function that I described as an infinite series of psi's times another psi, and I can get out what my constants are. So my Fourier series depended on me saying that it is this wave function, and then I have this extra constant out in front, and my method for determining the constant is this expression. Okay, so these 4 things that we just talked about, these are general. This is not just for an infinite square well. This is for any, well, like pretty much any potential. So it doesn't depend on that potential having that shape. So a lot of these proofs are going to be waiting until chapter 3, so that's why I'm going to hold off on getting too much into them now, because we will go over them later. Okay, then we have things like our stationary states. So if we wanted to go back to our complete wave function, we know that that guy was just going to be whatever our function was in x times e to the negative IE over h bar times t. So they just plug that in here. This was psi of x, and this right here is e to the negative I energy h bar over t. All they did was use energy equals n squared pi squared. We had h bar squared, but then it was divided by an h bar, and then 2 times m times a squared. Yep, 2 times m times a squared. Okay, so then this gives us our most general solution, where we expressed our psi as the series, an infinite series of solutions, and then times that energy, our phase factor term or our time-dependent term. Okay, so there's your solution. You can check it, which Griffiths recommends that you do, which I don't mind either. You can always, it's always good to plug in zeros when you're checking things. So if we plugged in t equals 0, we just get our psi of x term back. And we just get our sine wave. Okay, this might have been a little technical, probably, to say the least, but this is really like your heart of a lot of quantum mechanics, is this infinite square well. This is where like you get all these insights, such as discrete energy levels. The whole fact that it's quantized is coming from this example. If we have bound states in a limited cavity, we can only have a limited number of waves that fit inside of it. So this is the like if you hear about quantum mechanics and it kind of sounds like it's magic, a lot of it is coming from just trying to explain like the sort of quirkiness that comes from this solution. You know, we know our particles trapped in a well. There is a non-equal probability of finding it in different places of the well, depending on the energy state. Like, for example, a particle in the first state, n equals 1, you are very likely to find the particle in the smack middle of the well. If we are in the next excited state, n equals 2, we are now not very likely to find it in the middle of the well. So things like that. That's where all these come from. It doesn't mean anything's possible. It's still probability, but it's probably not as cool as you thought. It's probably much more boring than you thought, but it's still a really great example. Okay, and then the next things that we're going to do in other videos is we're going to do all these problems for infinite square wells. And if you were wondering, well, why does it have to be a sine wave? Because it starts at, you drew your potential to be going from 0 to a, and then you only throw out the cosine solutions because you had it have to equal 0 at psi equals 0. Yeah, that is arbitrary, and you can do it another way. You can do it with the freaking cosine, and what do you know? That's going to be one of your problems. I believe it is problem 2.4. There you go. You're going to do it with the well centered instead of having your well be a sine wave. So there. Yeah, it's going to be there. So don't worry. Don't flip out. It's going to be there. Yes, it was an arbitrary distinction. Personally, I like sine waves better, but whatever. It literally does not matter. You get to choose your own coordinate system. It's going to be one or the other. There's no reason to choose your boundary conditions in a way that's going to make your life harder. Alright, so that's it for square wells. And now we are prepared for the next 7 problems before moving on to harmonic oscillators.